Good morning, everybody. My name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my series of lectures on the concept of two-port network. In my first lecture on two-port network, I am going to discuss some basic concepts such as a standard equation of Z, Y, H and ABCD parameters, their applications, as well as we are going to derive the condition of reciprocity and symmetry in case of those four parameters. In my second lecture on two-port network, I am going to discuss some tutorials based on Z, Y, H and ABCD parameters. And in my third and last lecture, I'm going to derive the interrelation between various parameters. So in today's lecture, we are going to see some of the basic concepts regarding two-port network. So first, the definition of port is nothing but a pair of terminals through which a signal may enter or leave a network. So here, as indicated, 1 dash is nothing but a port. Here, since we have only one pair of terminal, this network is called one port network. Similarly, two-port network is nothing but an electrical network consisting of two separate ports. One is used as input and another one is used as output. So here in this representation, as you can see, 1 dash is input and 2 dash is output. Since this network has two ports, this network is called two-port network. Applications of two-port network. So the main purpose of studying two-port network are as follows. These networks are generally used for communications, control systems, power electronics, as well as in power systems. So after knowing the parameters of a two-port network, it will help to analyze and understand the overall system. So here we have four quantities relating to two-port network, that is V1, V2, I1 and I2. V1 indicates the voltage at input port, V2 indicates voltage at output port. Similarly, I1 indicates the current in input port and I2 indicates the current at output port. So among these four quantities, always two quantities are dependent and other two quantities are independent. So the various terms that relate these four quantities are called parameters. So the network parameters can be broadly classified into 6 categories: Z parameters, Y parameters, H parameters, ABCD parameters or transmission parameters, inverse H parameters and inverse transmission parameters. So out of these 6 parameters, in today's lecture and in preceding lectures, we are going to discuss regarding the basic 4 parameters, that is Z, Y, H and ABCD parameters. So first, Z parameters are also called as impedance parameters. The main application of these parameters they are commonly used in synthesizing of filters, also in design and analysis of impedance matching networks. They are also widely used in power distribution networks. The standard equations for Z parameters or impedance parameters are V1 is equal to Z11 I1 plus Z12 I2. The second standard equation for Z parameters is V2 is equal to Z21 I1 plus Z22 I2, where I1 I2 are independent variables, whereas V1 V2 are dependent variables. So as you can see that these parameters can easily be calculated either by putting I1 as 0 or I2 as 0. Current 0 indicates that open circuit. So I1 indicates opening of input port, I2 indicates opening of the second port. So either by opening the first port or the second port, these four parameters, that is Z11, Z12, Z21 as well as Z22, can be calculated. Hence, these Z parameters are also called as open circuit parameters. So first let us consider the first case, that is input port is open circuited. So when I consider I1 to be 0, these two expressions become 0. So I will get the value for Z12 to be V1 by I2. Its units are ohms, and similarly from second expression Z22 will be nothing but V2 by I2. Units are also ohms. So where Z12 is called open circuit reverse transfer impedance and Z22 is called open circuit output impedance or driving point output impedance. The second case, let I2 be 0. So when I open circuit the second port, these two terms become 0. So when those two terms become 0, I'll get the expression Z11 to be V1 by I1. Units are ohms, and Z21 is V2 by I1. Its units are also ohms. Where Z11 is called open circuit input impedance or driving point input impedance, and Z21 is called open circuit forward transfer impedance. So from these two standard equations we can easily obtain the general equivalent circuit for Z parameters. If I can apply KVL to both the first loop as well as the second loop, you can observe that I'll get the two standard equations for Z parameters. Next is the Y parameters or admittance parameters. So these also find the same application as in Z parameters. That is, these are commonly used in synthesis of filters, also used in design analysis of impedance matching networks, as well as power distribution networks. The standard equation for Y parameters are I1 is equal to Y11 V1 plus Y12 V2. Similarly, I2 is equal to Y21 V1 plus Y22 V2, where V1, V2 are independent variables and I1, I2 are dependent variables. So here, as you can see, these four parameters can be found out either by making V1 as 0 or V2 as 0. V1 indicates short circuiting input port, V2 0 indicates short circuiting second port. So either by short circuiting first port or second port, I can easily find the values for Y11, Y12, Y21 as well as Y22. Hence these parameters are also called as short circuit parameters. So first let me consider the short circuit of in the input port. So while making V1 as 0, these two terms become 0. So I'll be left with Y12 I1 by V2. Units are Siemens or Mohs. Similarly, Y22 will become I2 by V2. Its units are also Mohs or Siemens, where Y12 is called short circuit reverse transfer admittance and Y22 is called short circuit output admittance or driving point output admittance. So the second case, I'll consider short circuit of the second port V2 as 0. So when I make V2 0, these two terms become 0. So I'll get the values for Y21 to be I2 by V1 of units Mohs or Siemens. Similarly, Y11 will be I1 by V1 of units Mohs or Siemens. where Y21 is called short circuit forward transfer admittance and Y11 is called short circuit input admittance or driving point input admittance. So using those two standard equations, I can get the generally equivalent circuit for Y parameters. So if I apply nodal analysis at both first port as well as the second port, I'll get those two standard equations for Y parameters. So next is the H parameters or hybrid parameters. So the applications of hybrid parameters is generally used for describing electronic devices like transistors and op-amps. The standard equations for H parameters or hybrid parameters are V1 is equal to H11I1 plus H12 V2, and second equation is I2 is equal to H21I1 plus H22 V2. Here I1 and V2 are independent variables and V1 and I2 are dependent variables. Here you can see the H parameters can be calculated either by making I1 as 0 or V2 as 0. I1 0 indicates open circuiting the port 1 and V2 0 indicates short circuiting port 2. So in other words, either by open circuiting port 1 or by short circuiting port 2, I can find the values of H parameters. So it is the mixture of what we have seen in Z parameters as well as Y parameters. Hence it is since it is a combination of those two conditions, these are generally named as hybrid parameters. So in first case, let us consider open circuiting port 1. So when I open circuit port 1, these two terms become 0 and I'll get the values of H12 to be V1 by V2. Since it is the ratio of similar quantities, there are no units for H12. Similarly, H22 will be I2 by V2. Since it is the ratio of current by voltage, its units are mhos or Siemens. Where H12 is called open circuit reverse voltage gain and H22 is called open circuit output admittance. The second case, now let's consider short circuit of the port 2. So when I short circuit port 2, these two terms become 0. I'll be left with H11 to be V1 by I1. Its units are ohms, and H21 will be I2 by I1. Since it is the ratio of similar quantities, there are no units for H21. Where H11 is called short circuit input impedance and H21 is called short circuit forward current gain. So the generally equivalent circuit for H parameters is as follows. So using those two standard equations, if I apply mesh in the first part of the circuit and if I apply nodal analysis in the second part of the circuit, I'll get those two standard equations for H parameters. So next is the ABCD parameters or transmission parameters. The application of these parameters are generally used in the design of telephone systems, microwave networks as well as radar. These are also useful in the analysis of transmission lines. The standard equations for ABCD parameters are V1 is equal to AV2 minus BI2, I1 is equal to CV2 minus DI2, where V2 and I2 are independent variables, whereas V1 and I1 are dependent variables. So here these parameters can be found either by making V2 as 0 or I2 as 0. V2 0 indicates short circuiting port 2 and I2 0 indicates open circuiting port 2. So in other words, either by short circuiting or open circuiting port 2, we can easily find these two parameters. So the other names for these parameters are chain parameters as well as T parameters. So in first case, if I consider short circuiting of port 2, these two terms become 0. Therefore, B is equal to minus V1 by I2. Units are ohms, and D is equal to minus I1 by I2. Since it is the ratio of similar quantities, it has no units, where B is called negative short circuit transfer impedance and D is called negative short circuit current gain. In the second case, when I open circuit port 2, these two terms become 0. Then A is equal to V1 by V2. Since it is the ratio of similar quantities, it has no units. C becomes I1 by V2. Its units are mhos or Siemens, where A is called open circuit voltage gain and C is called open circuit transfer admittance. So these are regarding the standard equations as well as applications of the four basic parameters Z, Y, A, B, C, D and H parameters. So now, before we derive the expression for condition of symmetry as well as reciprocity, first let us see what is reciprocal network as well as symmetric network. So the definition for reciprocal network is nothing but if the ratio of excitation to response is same even though we interchange their positions, then such a network is called reciprocal network. If the impedance measured at input port is equal to the impedance measured at output port with remaining ports open circuited, that is, if I measure impedance at input port, the output port should be open circuited. Similarly, when I measure impedance at the output port, the input port should be open circuited. So when these two values are equal, then such network is called symmetric network. So as the definition of reciprocal network, if I take you back to the definition, the ratio of excitation to response must be same even though we interchange their positions. Then such network is called reciprocal network. The excitation to response. Okay, let me consider a two-port network. So in first case, I will consider excitation at the input port, and after short circuiting the output port, I will consider the response in the second port. So in this case, the ratio of excitation to response is V1 by I2 dash. Now I will interchange the positions of excitation and response. That is, as you can see, I have considered excitation at the second port, and now I have short circuited the input port and considered the response in the input port. Okay, so here in this case, the ratio of excitation to response is V2 by I1 dash. So if these two ratios are equal, then that two-port network we consider as reciprocal network. So now we shall derive this reciprocal condition for all the four parameters, that is Z, Y, H and ABCD parameters. So the condition of reciprocity in case of Z parameters. So here I have considered excitation in the input port, and after short circuiting the output port, I have considered the response in the second port, that is I2 dash. Okay. So as you can see from the direction of I2 and I2 dash, both are opposite to each other. Hence the condition I2 is equal to minus I2 dash. Since I have short circuited the port 2, V2 value will become 0. The values at the input port will remain unaffected. So in this condition, my aim is now to find the ratio of V1 by I2 dash. Now we know the standard equations for Z parameters. V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z21 I1 plus Z22 I2. I'll consider them as equations 1 and 2 respectively. So here, applying these above conditions in the two equations, we get V1 is equal to Z11 I1 minus Z12 I2 dash, since I2 is equal to minus I2 dash. I'll consider that as the third equation. And next, the second equation becomes 0 is equal to Z21 I1 minus Z22 I2 dash. Okay. So here my aim is to find the ratio of V1 by I2 dash. So from third equation, as you can see, I have the term V1 as well as I2 dash. So in order to get the ratio, I should eliminate I1 from the third equation, and that I can eliminate by using the second equation that you have obtained. That is, in this case, if I rewrite my second equation, I'll get the expression for I1 to be Z22 by Z21 into I2 dash. So after substituting the fourth equation and third equation, I'll get my required ratio V1 by I2 dash. So on simplification, the ratio of V1 by I2 dash will be Z11 Z22 minus Z12 Z21 divided by Z21. I'll consider that as my fifth equation. The second case, now we have to interchange the positions of excitation and response, isn't it? So second port, I'll consider the excitation to be V2, and after short circuiting the input port, I'll consider response as I1 dash. So my aim in this case is to find the ratio of V2 by I1 dash. So the standard equations we know for Z parameters are as follows. So these conditions, that is V1 is equal to 0 and I1 is minus I1 dash, I'll substitute in the first two equations. So the first equation becomes 0 is equal to Z11 minus I1 dash plus Z12 I2. And the second equation becomes V2 is equal to Z21 minus I1 dash plus Z22 I2. So since my objective is to find the ratio of V2 by I1 dash. See, from fourth equation, I have the terms V2 as well as I1 dash. I just need to eliminate I2 from this equation, and that can be done by using the above expression. So from this expression, I can rewrite my equation to be I2 is equal to Z11 by Z12 into I1 dash. I'll substitute this third equation in fourth equation, which will give me the required ratio, that is V2 by I1 dash. On simplification, which will give me Z11 Z22 minus Z12 Z21 divided by Z12. I'll consider that as fifth equation. So now I have obtained the ratio in both the cases. So for this to satisfy the condition of reciprocity, the ratio of V1 by I2 dash should be equal to the ratio of V2 by I1 dash. So I will equate the conditions that I have obtained in both the cases. So on simplification, we get the condition of reciprocity for Z parameters to be Z12 is equal to Z21. So now for Y parameters. So here in first case, similarly I considered excitation in the input port and the response I have considered at the output port. So the standard equations for y parameters are as follows, which I consider as equation 1 and equation 2. Now I'll substitute these conditions, that is V2 is equal to 0 and I2 is equal to minus I2 dash in both the equations. When I substitute the equation, the first equation becomes I1 is equal to Y11 V1 and the second equation becomes minus I2 dash is equal to Y21 V1. My objective is to find V1 by I2 dash, which I can directly get from the fourth equation, which is V1 by I2 dash will be minus 1 by Y21, which I consider that as fifth equation. In second case, I am considering excitation in the output port and response in the input port. Here also the standard equations for y parameters I consider as equations 1 and 2. Here the conditions that I need to substitute is V1 is equal to 0 and I1 is equal to minus I1 dash. So on substituting these two conditions, the first equation becomes minus I1 dash is equal to Y12 into V2 and the second equation becomes I2 is equal to Y22 V2. My objective is to find V2 by I1 dash. So that directly I'll get from the third equation, which is minus 1 by Y12. Hence, in both the cases we have obtained the ratio. So now let us equate these two expressions. From the condition of reciprocity, these two ratios should be equal. So when I equate these two expressions, the condition of reciprocity in case of y parameters is nothing but y21 is equal to y12. So next is H parameters. So here also I consider excitation in the input port and response in the output port. Since I am short circuiting the output port, V2 is equal to 0 and I2 will be minus I2 dash. So standard equations for H parameters I'll assume to be the equations 1 and 2, substituting the above conditions in both the equations. The first equation becomes V1 is equal to H11 I1. The second equation becomes minus I2 dash is equal to H21 I1. My aim is now to find the ratio of V1 by I2 dash. So here in place of I1 I need I2 dash. Thereby, so I can rewrite this equation to be I1 is equal to minus 1 by H21 into I2 dash. I'll consider that as fourth equation. Now I'll substitute the fourth equation in third equation. I'll get my required ratio V1 by I2 dash to be minus H11 by H21, considering it as equation 5. So the second case, I'll consider excitation at the second port and response in the first port. So since response is considered in the first port, V1 is 0 and I1 is minus I1 dash. Considering the standard equations for H parameters to be equations 1 and 2, substituting these two conditions in the first equation as well as second equation, the first equation becomes 0 is equal to H11 minus I1 dash plus H12 into V2. The second equation becomes I2 is equal to H21 into minus I1 dash plus H22 into V2. Now my aim, since it is to find V2 by I1 dash, I can directly obtain the ratio from third equation. So therefore from directly third equation, the ratio of V2 by I1 dash is nothing but H11 by H12. Now since we have obtained the ratios in both the cases, now we have to equate these two expressions, since the condition of reciprocity is V1 by I2 dash equal to V2 by I1 dash. So upon substituting the above conditions that we have obtained, the condition of reciprocity in case of H parameters is obtained to be H12 is equal to minus H21. So next is the ABCD parameters. First let me consider the excitation at the input port and response at the output port. So since response is considered at output port, we'll get the condition V2 is 0 and I2 to be minus I2 dash. So considering the standard equations of ABCD parameters as equations 1 and 2, on substituting the above conditions in these two equations, the first equation becomes V1 is equal to minus B into minus I2 dash. The second equation becomes I1 is equal to minus D into minus I2 dash. Since now my aim is to find the ratio of V1 by I2 dash, I can directly get it from the third equation. So from the third equation, V1 by I2 dash will be nothing but B. In the second case, when I consider my excitation to be at output port and response in the input port, V1 is equal to 0 since it is short circuited, and I1 will be minus I2 dash. Considering the standard equations of ABCD parameters as equations 1 and 2 and substituting the above conditions, first equation becomes 0 is equal to AV2 minus BI2, and the second equation becomes minus I1 dash is equal to CV2 minus DI2. So since my aim is to find V2 by I1 dash, so from fourth equation I can easily get the ratio of V2 by I1 dash provided I eliminate I2, and that I will eliminate using the above expression. This expression I can rewrite as I2 is equal to A by B into V2, which I considered as third equation. So after substituting the third equation and fourth equation, I'll get my reside ratio, that is V2 by I1 dash is B by AD minus BC. So after obtaining the expressions in both the cases according to condition of reciprocity, I should equate both the expressions, that is V1 by I2 dash and V2 by I1 dash. So on equating both the expressions that you have obtained, I'll obtain the condition of reciprocity for ABCD parameters to be AD minus BC is equal to 1. Hence, the condition of reciprocity obtained in case of ABCD parameters is AD minus BC is equal to 1. In case of H parameters is H12 is equal to minus H21. In Y parameters it is Y21 is equal to Y12, and Z parameters it is Z12 is equal to Z21. So let us consider the symmetric network. From the definition of symmetric network, I have seen before, if the impedance measured at the input port is equal to the impedance measured at the output port, with the remaining ports open circuited, then such network is called symmetric network. So first case, when I consider impedance at the input port, the output port should be open circuited. Hence in this case I2 is made 0, and when I2 is made 0, I'll measure the impedance at the input port and find the ratio of V1 by I1. In second case, when I open circuit the input port, I'll measure the impedance at the output port and find the ratio of V2 by I2. So when these two ratios become equal, then I say the given network is a symmetric network. So now let us derive the condition of symmetry for all the four parameters. So first let us derive the symmetric condition for Z parameters. So here the standard equations for Z parameters I consider as equations 1 and 2. So now on substituting the condition I2 0 in both the equations, these two terms become 0. Since my now objective is to find the ratio of V1 by I1, I'll get that directly from first equation as V1 by I1 to be Z11. The second case, Now I'll open circuit the first port and substitute the condition I1 0 in both the equations. So when I1 becomes 0, these two terms become 0. Since my objective is to find the ratio V2 by I2, I'll get it directly from the second equation to be Z22. So on equating these two conditions which we have obtained, so according to condition of symmetry, V1 by I1 should be equal to V2 by I2. Hence for Z parameters, the condition of symmetry is Z11 is equal to Z22. Next is the Y parameters. So the same condition. Here the standard equations I assume to be equations 1 and 2 and substituting I2 to be 0. And I substitute I2 to be 0. The first equation becomes I1 is equal to Y11 V1 plus Y12 V2. And the second equation becomes 0 is equal to Y21 V1 plus Y22 V2. Here my objective is to find the ratio of V1 by I1, and that I can obtain from third equation provided I eliminate V2. So that V2 I'll eliminate using this equation, which I rewrite as V2 is equal to minus Y21 by Y22 into V1. This I'll substitute in the third equation. So when I substitute the fourth equation in third equation, I'll get my desired ratio V1 by I1 to be Y22 divided by delta Y. The second case, I'll consider open circuit of the port 1 and substitute in the two standard equations of Y parameters. So the first equation becomes 0 is equal to Y11 V1 plus Y12 V2, and the second equation becomes I2 is equal to Y21 V1 plus Y22 V2. So there is no change in the second equation. Since my objective is to find V2 by I2, I'll get that from the fourth equation provided I eliminate V1, and that V1 I can eliminate by using the above expression, which I can rewrite as V1 is equal to minus Y12 by Y11 into V2. Substituting the third equation and fourth equation, I'll get my desired ratio V2 by I2 to be Y11 divided by delta Y. So after obtaining the expressions of impedances in both the cases, according to condition of symmetry, these two ratios should be equal, and hence we can conclude that the condition of symmetry in case of Y parameters is Y11 is equal to Y22. So the standard equations for H parameters are as follows, which we consider as equations 1 and 2. So here also I'll open circuit the second port and substitute the value of I2 0 in both the equations, which will give me 0 is equal to H21 I1 plus H22 V2 from the second equation, and the first equation is V1 is equal to H11 I1 plus H12 V2, which will remain the same. Now since my objective is to find V1 by I1, so I have to eliminate V2. That I can eliminate by using this expression, that is V2 is equal to minus H21 by H22 into I1. Substituting this in the first equation, I'll get the desired ratio V1 by I1 to be delta H by H2. The second case, I'll open circuit the input port and substitute in the standard equations, which will give me directly V2 by I1, because since I1 is 0, both the terms will get can become 0. So directly from the second equation I'll get V2 by I2 to be 1 by H22. So equating the both relations that we have obtained, we'll obtain the condition of symmetry for H parameters to be delta H to be equal to 1. And lastly, the condition of symmetry for ABCD parameters. So here also I'll substitute I2 0 in the above equations, which will give me V1 is equal to AV2 from first equation and I1 is equal to CV2 from second equation. Since my objective is to find V1 by I2, I'll divide both the expressions, third equation as well as fourth equation, which will give me V1 by I1 to be A by C. So the second case, I'll consider I1 to be 0, that is open circuiting the first port. The standard equations are considered as equations 1 and 2. So when I substitute the condition in second equation, 0 is equal to CV2 minus DI2. Since my objective is to find the ratio of V2 by I2, I'll get it directly from the second equation, that is V2 by I2 will be D by C. So equating both the relations that we have obtained, and we derive and come to a conclusion, the condition of symmetry in case of ABCD parameters to be A is equal to D. Therefore, the condition of symmetry in Z is Z11 is equal to Z22. For Y parameters, it is Y11 is equal to Y22. For H parameters, it is delta H is equal to 1. That is H11 H22 minus H12 H21 is equal to 1. And in case of ABCD parameters, A is equal to D. So this concludes my first lecture on the two-port network, the basic concepts, their standard equations, applications, as well as deriving the condition of reciprocity as well as symmetry. In the next lecture, we shall see some tutorials based on these four parameters. Thank you.